Okay, so this section of the notes says origin of modern history. So this is kind of the history that has kind of led to where we are now. Some of the big names in historical astronomy, that sort of thing. So like I said, we won't go through all these today, but we'll go through some of them. All right, first thing, just definition of astronomy. So, the science that studies the universe, anything you find in the universe that's out in space. Pretty broad, broad branch of science that definitely has a list of specialties and focuses. Some scientists are just studying planets, some just study stars, all that stuff. So. All right, first thing, a couple of terms that are pretty important. Geocentric and heliocentric. First one, geocentric. Geo, meaning Earth, and then centric, it's kind of like it sounds, it's like center or central. So the geocentric model, this is kind of an older way of viewing the solar system and kind of the known universe. At that time, the Earth's at the center of it, and everything orbits the Earth. So it's a geocentric model. A little more modern, at least officially, way of viewing the solar system, the heliocentric. So helio, that means sun, and then again centric, it's just the center. So a sun-centered solar system. So the sun's in the middle, and then all planets orbit the sun. So we have, I guess I'll touch on that here in a sec. All right. These are just a couple of different kind of depictions of those different types of models. So we have geocentric with the Earth in the middle. Then we have heliocentric with the sun in the middle. All right. I guess I'll touch on this and then I'll kind of restate it. So with a lot of things in science and astronomy, there are a lot of people that kind of get credit for certain things, discoveries or concepts or things like that. And I'm in no way saying that these people are the first ones to think of this. I'm not saying, oh, they were the first to discover that. They were the first. Some of these that you have to have, pretty high-tech instruments to find. Probably a little more likely, but I'm pretty confident that there were people, before the Greeks that did recognize these things that Ptolemy did, and and others. But this is who gets credit for it officially, I guess, or officially with us currently. So, but Ptolemy was a Greek, almost 2,000 years ago. He kind of named or came up with the term planets. Just this planetos for wanderers. He noticed these points moving through the night sky. He also explained retrograde motion. We won't go into it a ton. His explanation was incorrect, but I mean, it's almost 2,000 years ago. I mean, lots changed since then. So all retrograde motion is, it's like it says, the apparent backward motion of a planet. So it just looks like the planet is moving backwards. It's not actually moving backwards. It just looks like it. With the retrograde, the retro, a prefix means like reverse or backwards. So just like there's kind of a lot of it going around. They're the newest retro Jordans or something. yeah, I mean, they're brand new shoes. They were just produced or whatever, but you know, it's an old style. They kind of went backwards in time to get that style and then kind of reintroduced it. There's been a lot of that in cars lately. You know, they'll go back and take design cues from, you know, past design models and all that stuff. So retrograde motion, it looks like it's moving backwards, but it's not really moving backwards. And we have a little animation, and I don't know, this thing is just creeping along. I don't know what the deal is with this, but it shows the path that Mars takes through the night sky. You see the date down here in the lower right. So this is every 2 days, so like November 14th, 16th, 18th, 20th. So you would expect, you know, a planet to kind of take a path that's, you know, pretty much straight line. You know, it's on its orbit. We're on our orbit. This is, you know, something that seems pretty typical. But then here shortly, retrograde motion starts to kick in, where it looks like the planet Mars is moving backwards, but I mean, in actuality, it's not moving backwards. So it's kind of slowing down. Now this is retrograde motion, where it looks like Mars is moving backwards. Obviously, the planet has not stopped orbiting the sun and started moving backwards. I mean, it's just not doing that. This continues for a little bit, and then it'll change direction again, and then start moving in its original direction. But for this period of time where it's moving backwards, that's retrograde motion. Like I said, I don't know why this thing's creeping along. You check the setting or something. I don't know. All right, so now this is starting to go back towards its original direction. Like I said, that section was retrograde motion. All right, so there are a couple of different explanations. The top one was Ptolemy's explanation, was that the planet on the orbit wasn't just moving, it was actually orbiting something as it orbited the Earth at that time. And that's why we saw that the retrograde motion. What's actually happening is because the Earth is on its orbit and Mars is on its orbit, it's just how it appears as we're looking at Mars, because, you know, two moving objects, it just appears that the Mars is moving backwards, but it's not. It just all has to do with your point of view, like where you're looking from. So it's retrograde motion. All right. So this guy, he's an important guy. I would remember the name. So this is Nicholas Copernicus, and in the 1500s, he was credited with coming up with the idea of the heliocentric model. Like I said, I'm not saying he's the first guy to ever think of this, because I would be willing to bet pretty much anything that he's not. I mean, there are tons of cultures way older than ours that knew way more than we give him credit for. But it's just that he gets credit for it. You know, he's the one that kind of stuck his neck out there, documented it, and kind of made it official, I guess. In the 1500s, this was not a popular concept. The church, which was very powerful at the time, did not like this, because their teachings were that the Earth was the center of everything and everything revolved around the Earth. So to go against that was could be dangerous. It could be life-threatening. You know, if you're saying things that the church didn't like and you continued to say those things, it was not super uncommon for them to silence you by killing you. So, but he based, you know, this idea, this concept, this model on observations that he had made, that other scientists had made, and the geocentric model just didn't add up. You know, the way things, the way the observations, you know, were, and that information, it just didn't work out correctly if the Earth was at the center. But if you had the sun in the center, then things fell into place and they worked, you know, just as they were being observed. So I said, he's the main guy. You know, he gets the credit for that. Even though, I mean, like I said, I'm supremely confident he was not the first person to ever think of that. So, next guy, Tycho Brahe, Danish guy. That means he's from Denmark. He's not a Danish, or he's not, you know, coffee cake or pastry. He may have liked it, I don't know. Also, this is a commemorative stamp. He did not live to be 400 years old. The 1546 to 1946, that wasn't like his birth date, and then the day that he died, it was issued 400 years after his birth. So, in case anybody noticed that, he spent a lot of time making a lot of observations. His big thing was he was really, really good at making telescopes, and he was really good at making scientific instruments. So at this point in time, he was making the best stuff out there. He was making the best equipment that was available. And astronomy is one of those things that if you have better equipment, you're going to get better information. You're going to be able to see things more clearly. You're going to be able to see further than somebody else that has a telescope that's not, you know, as good. So because he had the best stuff, he was getting some of the best information. And, you know, he kept very detailed notes and logs and all kinds of stuff. Because he had the best stuff, that also made him popular with other scientists, because, I mean, if somebody has the best stuff and the coolest toys and the nicest equipment, other people, I mean, they want to play too. I mean, they want to be able to use the best stuff as well, you know, especially if they know that this good stuff's out there, but they're still using stuff that isn't as good. I mean, made him kind of a popular guy in the science world. So one of the guys that worked with him was Johannes Kepler. Huge name in physics, huge name in astronomy, all that. There's tons of stuff named for Kepler. I mean, there are planets named for Kepler. There's a space telescope named for Kepler that's looking for Earth-like planets, which basically means that it has liquid water on the surface, because all life that we know of requires liquid water. Not to say that there aren't life forms that don't need liquid water, but we don't know of any. So we're looking for those, and like I said, Kepler's the big telescope that's looking for that. So if they find a planet that has liquid water, then they name it Kepler, and then some series of numbers and all that. So, so he worked with Brahe, you know, again, recorded a lot of good information. Came up with these 3 laws of planetary motion. The first being that orbits are elliptical. Orbits are elliptical. So they're not perfect circles. They're an ellipse. They're kind of an oval. It's kind of, you know, kind of squished down. Also, and I'll get into this more later, this diagram is not accurate at all. I mean, some of the basics are, but there are issues. So orbits are elliptical. That's his first law of planetary motion. Kepler's second law is that planets move faster when they're closer to the sun. I'll mention this again later, but the force of gravity.
Good morning, North Central. This is Ms. Palacios. Teachers and students, pardon the interruption, but there your treasurer, Lucy Neal. and Secretary Lillian Henninger. For the junior class, Paulina Cruz, Vice President Maria Barrios Bustos, your treasurer, Lauren Fox, Secretary Cindy Johnson, and the student council officers for next year, your president is Paris Robinson, Vice President Namara Maciel Manzano, Secretary Lily Connor, and Treasurer Sadie Schmidt. Congratulations to you all. Thank you so much.
All right, sorry about that. So yeah, I'll mention this again, but one of the things with gravity is it's dependent on distance. So the closer you are to something, the more gravity there is, or the stronger gravity is. Further away, the weaker it is. So like with us, we're right on the surface of the Earth, gravity is pretty strong. The further away you get from Earth, the weaker that gravity gets. So the closer to the sun that the Earth gets, the faster it moves, and then the further away, the slower it moves. The third law, which we're not going to get into in case anyone was curious, has to do with the ratio or proportion of the distance from the sun to the time it takes to orbit. There's a relation, and that's the third law. But like I said, we're not going to go into it. This little animation, it just shows the orbits and all that stuff. Phases of the moon, the blue thing moving around the outside is the date, which is hard to read, is obviously not to scale or distance, but I mean, they're in the correct order, but so yeah. Another thing Kepler came up with is the astronomical unit. Basically just kind of a shorthand way of writing down the distance from the sun to the Earth, the average distance, which is about 93 million miles. This diagram of the Earth's orbit is much more accurate. So can anybody tell me why we have the seasons? Why we have the seasons? Anyone? Good. The Earth's tilted. So the Earth's axis is not straight up and down, it's tilted. And that tilt points in the same direction all the time. So as it's going around the sun, sometimes it points towards the sun, sometimes it's, if the sun's back here, it's pointing away from the sun. So for us in the Northern Hemisphere, if we're looking in January, that's wintertime. But if you look at the distance in January, that's when we're actually closest to the sun. So if the seasons depended on the distance to the sun, that should be summertime, but it's not. It's winter. Just like in July 4th, that's when the Earth is furthest away from the sun. But that's summertime for us in the Northern Hemisphere because the Earth is tilted towards the sun. So this is a much more accurate depiction of the orbit of the Earth. Like I said, not perfectly circular, but it's pretty close. I mean, we're only, talking like 5 million kilometers off. And so it's like 3 million miles. I mean, it's not that much. I mean, it is, but when you're talking about 93 million, it's like if you're buying $1 million car, what's another $50,000 for, some option? Not that I would know personally, but I mean, I could speculate that if I were buying $1 million car, another $50,000 for this or that, I mean, what's it matter at that point? You're already spending that much. So, like I said, this is a much more accurate depiction of the Earth's orbit, and it backs up the whole thing of the seasons are because of the Earth's tilted on its axis. All right, Galileo, Italian guy. He made his own telescopes, used telescopes. He studied orbits. Moons of Jupiter, studied Venus, studied the phases of Venus because it has phases just like the moon does, because as it orbits the sun, you can see, different portions of the planet are illuminated by the sun at different times. So that was one of the things that he studied. Sunspots, it's kind of a weird phenomenon. We aren't completely sure why this happens, but they're cooler spots on the surface. So it might be something where, instead of being 10,000 degrees, it's, 7 or 8,000 degrees. It's still really hot. It's just not as hot. And they're different color. They're darker because, as we talked about before, depending on how much energy is in something, it gives off a different wavelength of light. Just like if if there's the oven burner, just sitting there, it's just, kind of dark black. You turn it on, it starts to get hot. It's going to turn red, and as it gets hotter, it's going to, turn more orange. There's more energy in it, so it's giving off a different wavelength of light. So that's 1 second. So that's what I thought that this was kind of cool that on this diagram, right down here, that little dot, that's about the size of the Earth. So these sunspots are huge compared to the Earth. I mean, many, many, many times larger than the Earth itself. Yeah, it's kind of cool. All right. So a few more now. Isaac Newton, English scientist. He's the one that's kind of credited with, I don't want to say discovering gravity, because I mean, everybody experiences gravity all the time, but he kind of explained it a little bit and that sort of thing. So not so much discovered it. He also invented calculus, the math, the branch of or field of math, calculus. I mean, he invented it to, describe gravity and movement of things in space. And one of the things with gravity, like I mentioned, large mass equals large gravity. So if something's really big, it's going to have, a lot of gravity. And then distance. So if there's, big distance between things, not much gravity, just close together a lot. Hubble, Edwin Hubble. So this is who the Space Telescope's named after. American scientist that studied, like I said, the expansion of the universe after the Big Bang. Gets into something called redshift. I might touch on that Tuesday. I don't know. Yeah, I mean, I'll touch on it.
Could you go back? One more. Thank you.
Redshift has to do with the Doppler effect. Like I said, I'll probably touch on it Tuesday to keep things moving. And Einstein, obviously very famous and talented physicist, and had to do a lot with it, explaining why things behave the way they do in space and the universe itself.
Sorry, could you go back to 22 or 21? One of those. Hold on. 22. All right, thank you.
So gravity's influence on orbits. Anytime anything's in orbit, there are two forces that are acting on that body. So there's one that wants that thing, we'll just talk about the Earth. There's one force that wants the Earth just to go off in a straight line out into space. And then there's the gravity of the sun pulling the Earth towards the sun. So the kind of the battle between those two forces is why we end up with the orbit that we're in. It's just like spinning, you're swinging something around on a string. If you let go, it's going to fly off in one direction or another in a straight line. The Earth wants to do that all the time, but gravity keeps pulling us in. So we end up with the orbit that we're on.